Okay. So last time that we met, I found the antiderivatives for these 6 functions. And what we did is we basically just said, okay, well, I know the derivatives for sine x, cosine x, tangent x, secant x, cosecant x, and cotangent of x. And because I know the derivatives, I can work my way back from the derivatives that I know and recover the original functions. So that's the logic that we used and how we found the first 6 rules of integration. If you weren't in class, this is the same thing that I covered in the first video that I posted on YouTube. So I'm going to start just with a simple example from this type of problem, and then I'll go on to the next couple of antiderivatives that we want to find. So in this example, we can find the antiderivative, so we can evaluate the antiderivative of 3 times secant of 9x tangent of 9x, right? And so this is just a warm-up for those of you who might not have looked at this. I have 2 participants with their hands up, so that's John and Mark. Do you actually have questions, or is that just a mistake?
No, I just forgot to turn it off, sorry.
All right, you can please lower your hand, and then if you have a question, you can raise it. Same thing for Khan. Okay, there you go. Okay. So we're going to evaluate this integral. We know that this is secant times tangent, so this looks like we're going to have to use this rule because the secant function and the tangent function are being applied to the same exact inside function, except the inside function is not just x, right? So that means I can't just say this is going to be secant of x. Now, for this type of problem, I can either do a substitution, or I can remember that because this is a linear function, I will just have to divide by the derivative of the inside, right? So if I do a substitution, I'm going to use, for example, u is equal to 9x, which means that du is equal to 9 times dx. And that means that if I want to replace just dx, I'm going to have du over 9 is equal to dx, right? And at this point, I know that if I wanted to replace my integral, I would have integral, the constant 3 should stay there. Then I would have times secant. And now all of the instances of 9x are going to be replaced by u. So that means secant of 9x is going to be secant of u, tangent of 9x is going to be tangent of u, and then dx is replaced by du divided by 9. And so 3 over 9 becomes 1/3. And this is the integral of secant of u times tangent of u with respect to u. At this point, I can actually use the rule that we found last time, which tells me that this is going to be secant of u plus c, which means that I can now back substitute u and write this as 1/3 times secant of 9x plus c. Okay, so this is like using the whole substitution. So this is my whole substitution. But I could have also realized that this is just a linear function, which means that I just had to find the antiderivative of secant times tangent, which is secant of 9x, and then divide everything by 9. So that means if I had done it the fast way, this would have been 3 times, and then I know that the antiderivative of secant times tangent is going to be secant of 9x. Now, because this is a linear function, I know that I can just divide by the derivative of this plus c, and I would have gotten the same answer. But this is only the case because this is a linear function. Okay, so this is just because it's a linear function over here. So that's why I can replace things easily. Okay. Do I have any questions about this problem, or is that okay for everyone? Okay, no hands up. That's good. All right, so We saw this type of problem last time. We had just the antiderivatives that were obtained from obvious derivatives. Yes, Lucas, there's a question? There's no question.
Can you just go back for a second?
Yeah.
I forgot to write the answer.
Oh yeah, okay, sure. All right, so for the second part, we're going to figure out how to write.
Yeah, that's good. Thank you.
That's good? Okay.
Yeah.
We're going to try to figure out how to find antiderivatives of the functions that we haven't found antiderivatives for yet. So like, for example, here we have the antiderivative of secant squared of x, but we still don't have the antiderivative of just secant of x, right? We also have the antiderivative of secant times tangent, but we don't have the antiderivative of just tangent of x. So that means I have these four antiderivatives here, which are lucky because I knew that they were derivatives of given functions, but I don't really know the antiderivatives of the most elementary trig functions, which are the ones over here. Right, so that's going to be the next step. I think in the last class that we had, what we did is evaluate the antiderivative of tangent of x dx. I'm going to just reproduce this here for those of you that weren't here, that weren't in class. So basically, what we want to do in this case is find the antiderivative of the function tangent of x, except of course, we are assuming that we only know these 6 antiderivatives here. Now, neither of these is going to help me, and I have the antiderivatives of cosine and sine, but I want the antiderivative of tangent of x. So what I'm going to do is I'm going to start by rewriting this as a function of sine and cosine, right? So that means we're going to have integral of tangent of x, which is given by sine of x over cosine of x dx, right? And at this point, I can actually try to use something because I know the antiderivatives and the derivatives for both sine and cosine. And so I might be able to use some of the information that I know in order to evaluate this integral. So over here, what I can realize is, okay, well, cosine is at the denominator and sine is at the numerator, which means that if I were to do, for example, a substitution, I would have to substitute, as usual, the thing that's at the denominator. So that's the first thing that I can try. If it works, it works. And if not, then I have to try something else. So I'm going to start by doing that substitution by using u is equal to cosine of x. And then du would be the derivative of cosine of x. So the derivative of cosine of x is negative sine of x dx, which is actually pretty nice because now I have the sine of x that I can replace there, right? Now, because I only have sine of x dx, I'm going to put a minus on both sides. I'm going to multiply both of the sides over here by -1, and I'm going to get that if I want to replace just sine of x dx, I'm going to replace it with minus du. And so now I can rewrite my integral over here as the integral of 1 over u times sine of x dx, which is replaced by minus du. So I'm going to put the du over here and minus. Now, at this point, according to you, what is the antiderivative of -1 over u? Hopefully everybody remembers. But this is going to be well, negative in front, and then this is going to be ln of absolute value of u. And if you've been doing your web work assignments, you'll realize that it's really important to put the absolute values, otherwise the answer is not baked. So this tells me that this is minus ln of u, but u was just a code for cosine of x, which means that this is minus ln of cosine of x in absolute value plus c. Does anybody have any questions about this? Is this clear for everyone? Okay, no raised hands. All right, so then the second part, so the antiderivatives for cotangent, cosecant, and secant are obtained similarly. I'm going to write the proposition that gives me the antiderivatives of all of those. This means just the rules for each one of them. And then we're going to do a lot of practice. Okay, so this is the proposition, integrals of trig functions. And this is part 2, because part 1 is the one that we did right before going on break. It's the part that is also already posted on YouTube. So that means I'm going to have rules 7, 8, 9, and 10. And so rule number 7 is the one that we just came up with, which was the antiderivative of tangent of x with respect to x. And that gives us negative ln of cosine of x plus c. Then you have the antiderivative of cotangent of x with respect to x is obtained in the exact same way. So the way in which you are going to find it is the same. So I suggest that you try to do this just as practice. It's exactly the same way to find the integral of tangent of x, except cotangent is sine over is cosine over sine and not sine over cosine, right? So the substitution is going to be different, but the logic is the same. And this gives ln of sine of x plus c. Then you have the antiderivative of secant of x with respect to x, and that's going to be ln of secant of x plus tangent of x plus c. And finally, the last one is going to be the antiderivative of cosecant of x with respect to x, which is going to be minus ln of cosecant of x plus cotangent of x plus c. Okay, so these are the last integrals of trigonometric functions that you'll be required to know. So as I said, the rules for finding 7 and 8 are very similar. So you just write them in terms of sine and cosine. For 9 and 10, it's a little bit trickier. Okay, so for these ones, if you want to try them on your own, what you have to do is to multiply by a smart 1. So I've talked about this before in the class, smart zeros and smart ones. Smart ones just mean that you have to multiply the numerator and the denominator, or multiply top and bottom by the same thing. So for the 9th integral over here, you're going to have to multiply and divide, or multiply numerator and denominator, by secant of x plus tangent of x, and then do a substitution. Okay, so if you want to show that expression, you're going to have to multiply and divide by secant of x tangent of x, and then do a substitution. For number 10, you're going to have to multiply and divide by cosecant of x plus cotangent of x, and then do a substitution. Okay, so these are the type of things that, okay, so this is just a trick, and I don't require that you know all of these types of tricks, but trying these with the hint that I've just given is actually going to be really helpful, because it will help you identify what type of substitutions you can do using trigonometric functions. So if you get a chance to do them, I really suggest that you do. All right, do I have any questions about these rules? Okay, no questions. So I'm going to start with a couple of examples, and then we're going to, so I'll start with a couple of examples, and I'll give you some time to work on them, and I think that will be it for the first part, and then I'll just ramp up the level of the examples. So for the next part, we're going to have example. And of course, as usual, evaluate the following integrals. The first thing that I'm going to ask you to evaluate is the antiderivative of cosecant of 1 minus 4x with respect to x. Okay, so you have 1 minute to work on this one. All right, so if you try to evaluate this integral, you'll see that this shouldn't actually be that much more difficult, because we have that the inside function is just a linear function, right? So that means that we're going to have that the antiderivative of this is going to be just the antiderivative of cosecant of x applied to 1 minus 4x, and then I'll just have to divide by the derivative of the inside, right? So the antiderivative of cosecant of x was just minus ln of cosecant of the inside function plus cotangent of the inside function. And then I'm going to have to divide by the derivative of the inside function, right? So here I'm going to divide by minus 4, and the inside function was 1 minus 4x. Plus a constant of integration in the end. Did anybody find this answer? Can you raise your hand if you found this answer? Okay. All right, that's good. There's like 5 or 7 raised hands. That's good. Now, can everybody please lower their hand? If you were starting to do a substitution, can you raise your hand? Okay. So if you did the full substitution, you should have chosen u is equal to 1 minus 4x. And you should end up with the same answer. It's just that it's not as efficient, right? So that just means you have the right answer, but if you are trying to solve problems fast, this is not necessarily going to be the best way. Now, as long as you understand it, it's completely fine. So like, usually I try to give you the most efficient way, because in tests and in finals, you need to do it the most efficient way. And I still think that that's the case. But for now, if you understand how to do it just based on the idea, then that's completely fine as well. All right, for the next one, I'm going to ask you to find the antiderivative or the integral of x times tangent of 4x squared. Okay, so 2 minutes to work on this. Okay, so at this point, we have x times tangent of 4x to the power of 2. Now, you might have realized that here we have 4x to the power of 2 inside the tangent function, which means that we can't just integrate the tangent function over here. We have to do a little bit more. So lucky for us, you know, the derivative of 4x to the power of 2 is going to be something times x to the power of 1. And I have an x to the power of 1 over here. So that means that if I were to choose this as my inside function, I would be able to get rid of the x here or use it in order to replace my du as well. So I'm going to start doing a substitution by using u is equal to 4x squared, right? In this case, that means that I would get du is equal to 8x dx, which means that if I wanted to replace just x dx, because I have x here and dx here, I'm going to replace that by du divided by 8. So this is x dx. Which means that at this point, I'm going to replace tangent of 4x squared as tangent of u. And then x dx can be replaced by du divided by 8. Okay. if I have tangent of u is equal to du over 8, that means that I'm going to have to just integrate this function, which is actually not too bad because I know that this is going to be minus ln of cosine of u. And this was divided by 8, so it has to be divided by 8 over here, plus c. And now I can actually replace u, which was just a code for 4x squared. So that means that I had minus ln of cosine of 4x squared, the whole thing divided by 8 plus c. All right, and this is the final answer that I have. Now, I want to just give you a warning because sometimes I think you'll try to look for solutions online and you'll find answers that are a little bit different, and that happens very frequently with trigonometric functions because there's a lot of equivalences between trig functions. Okay, so it's possible that if you try to find the solution of a problem like this online, you would get the answer that this is equal to ln of absolute value of secant of 4x to the power of 2 divided by 8 plus c. So you'll see the big difference here is that there's no minus in front anymore, and the inside function has changed into cosine and not into secant and not cosine, right? And that's because if we have minus ln of cosine of something, let's say cosine of x, this is the same thing based on the laws of logarithms. If I have, so here I'm going to write, if I have minus ln of some number a, the laws of logarithm tell me that this is the same as ln of 1 over a. So that means that I have ln of absolute value of secant of x, because secant of x is 1 over cosine, right? So this is how that result is obtained. So you have to be really careful when you try to look for answers online to get to be sure that you understand that some answers are going to be equivalent even though the result is not exactly the same. Okay, so these two things are equivalent even though they look like they're slightly different. Is that clear for everybody? Do I have any questions about this? Okay. So with no questions on this, I'm going to go to the next example. I have again a couple of minutes to solve it. Yeah, to just try to do something with this problem. So that's the antiderivative of secant to the power of 7 of x times tangent of x with respect to x. Okay, so you have maybe 3 minutes to solve this problem. All right, does anybody know how we should get started, or does anybody think that they did something that got them somewhere? Or is everybody kind of lost here? A bit lost. Good thing. It's a lot easier to get answers from people when they're at home and muted. So in this type of problem, we might as well try something. Okay, so we can try to do to integrate each of the pieces separately, although of course we know that that's not true, right? So like one thing that would be wrong is to try to just take the antiderivative of this and then the antiderivative of that separately, right? We know that we can't do that, otherwise there would be no point to either product rule or integration by parts. Instead, what we're going to try to do here is to find the antiderivative of this by doing a substitution. And the difficult part in this type of problem is to figure out which substitution to use, right? So there's a couple of options. We can use either secant of x as a substitution because we have a secant of x to the power of 7, or we can use tangent of x as a substitution. Now, secant of x is the one that is to the power of 7, right? So we might as well just substitute that term and see what we need in order to replace our du. So that's how I'm going to start the problem, just because this is the thing that's to the highest power, and we can see if that helps. So I'll have that u is equal to secant of x. Can I see a show of hands for those of you who tried this substitution, even if you didn't finish the problem? Just raise hands. And don't lower it until I tell you to lower it. Okay, so 8 participants tried to 9. Okay, 9 of you tried to do the substitution. That's a good reflex. Those of you who didn't might have tried an integration by parts, which is going to be really hard because we don't know how to find the antiderivative of this alone, right? Or if we find the derivative of this on its own, then we're actually just complicating the integral that we have. Everybody can lower their hands. So if we use just u is equal to secant of x, we know that du is going to be equal to the derivative of secant of x, which is just secant of x times tangent of x dx. And here's something that's going to happen a lot when we're doing trigonometric integrals, and is that, you know, the secant of x that we replaced, we know that this is going to be replaced by u, except I can't replace all 7 of them by u because I'm going to need one of them to replace the du, right? So that means I'm going to have to break this secant to the power of 7 into secant to the power of 6, and then another secant, because the second part I'm going to use in order to replace the du. So that means I'm going to rewrite this integral as the integral of secant of x to the power of 6 times secant of x times tangent of x dx. And the advantage of that is, of course, that now I can replace this with du. And we know that that's our priority. We always have to replace du first, and then whatever is left, we have to figure out in terms of u. So now we're going to have to replace each of the terms. Now I have that this is secant of x to the power of 6. I'm going to have the integral of u to the power of 6. And then secant of x tangent of x dx is replaced by du. Okay, so this is why it's important to find u and du everything before I try to replace things, because you really need to have a plan for everything in your integral. And at this point, you'll have that this is the same as u to the power of 7 divided by 7 plus c, which of course I have to then back substitute, and this is going to be equal to secant to the power of 7 of x divided by 7 plus c. Okay, do I have any questions about this problem? Okay, I see no hands. So in that case, I'm going to give you the following problem to solve, which is going to be the integral of, so from 0 to pi over 4 of secant squared of x times square root of 1 plus tangent of x with respect to x. Okay, so you can try to solve this one. Again, I'll give you 2 minutes. So what we're practicing is how to identify the technique that we need to use for each trig function. 2 minutes for this one. Okay, is there anybody that thinks they know how to start this problem at least, that would like to share your strategy? No, okay. So in that case, let's try to see what we can do in this case. We have a square root of something, right? So square root of 1 plus tangent of x. That means that this is 1 plus tangent of x to the power of something, which means it's a complicated function inside of a power. So that means it might be useful for us to try to substitute that thing that is inside the power. So I'm going to try to do a substitution. Now, another thing that should help me in realizing that my substitution is actually going to work is that the derivative of the inside function here will be the derivative of just tangent of x, which corresponds to secant squared of x, right? So that means that the substitution should be fairly easy to do. And then it's just a matter of actually finding the bounds. So I'll have that u is equal to 1 plus tangent of x, and du is equal to secant squared of x dx. Okay. So d is equal to secant squared of x dx. That means I can get rid of this. I can now replace the inside of the square root as well. But because this is a definite integral, I need to also change the bounds, right? So a is going to change, b is going to change. So I'm going to have a and b. And yes, so I'm going to have to change these. So that means I'm going to have 1 plus tangent of 0. And tangent of 0 is sine of 0 over cosine of 0, which is 0 over 1. So that means this is going to be 1. And b is going to be 1 plus tangent of pi over 4. And tangent of pi over 4 is equal to 1. So that means that this is 1 plus 1, which is 2. You should be able to find these easily if you know your unit circle, but you can, of course, always use your calculator as well. And in your calculator, you should get these results as long as you have set the calculator to radians. So remember, it's always in radians. In calculus, we've never used degrees. So if I do the substitution, I'm going to have that this is the same as the integral from 1 to 2 of square root of 1 plus tangent of x, which is u. And then secant squared of x dx can be replaced as du. Now, at this point, I can forget about my original integral, right? Because this is a definite integral, I have now changed the bounds, the function, and the du. So that means I can forget about the original integral, and everything is going to be expressed based on the new thing that I found over here. I don't have to back substitute because that's the whole point of changing the upper and lower bound. So here I'm going to get that this is u to the power of 3 on 2 divided by 3 on 2, evaluated between 1 and 2. So I can rewrite this as 2/3 times u to the 3 on 2 between 1 and 2, which is the same as 2/3 times 2 to the power of 3 halves minus 1 to the power of 3 halves, but 1 to the power of anything is just 1. Is this all right for everybody? Do I have any questions about this, or everyone okay with this? Okay, so in that case, you can start the next problem, which is x sine of x with respect to x. We're finding the antiderivative of that. I'm going to ask all of you to put your cameras on just so that I make sure that everybody's working. I know it's a bit of, anyway. I'm going to pause the recording though, so your images will not be in the recording. So does anybody have a clue what technique we should use? And maybe what you can do is, if you're shy to speak out loud, you can try to write it on the chat. That might help. Any idea on what technique we should use for this type of problem? No idea. I'm getting no input. So we can do substitution, but if we wanted to do substitution and we try to substitute x, that's not really going to help. If you try to substitute sine of x, we're going to need a cosine of x in order to substitute that, right? So it's not really going to help me that much to do substitution in this particular case. We don't have a function that is applied to some inside function anymore. So elimination, I'm not sure. Somebody's saying elimination. What does that mean? I'm not sure. The answer is no, especially because I don't know what that means exactly. Did anybody try something that they think worked? So basically what I could do here is if I just were able, yes, so if I just were able to get rid of x, my integral would be a lot easier to evaluate. And how do I get rid of x? I can differentiate it. So if I have to differentiate a piece, then that means I need to do integration by parts, right? So I'm going to choose v to be the function that I need to differentiate, which in this case is x. And that means that dv would have to be equal to dx, right? In the same way, that means that du would have to be equal to sine of x dx, which means that u would have to be the integral of that. So if my derivative is sine of x, my original function must have been minus cosine of x. At this point, I can actually try to evaluate this. Now, can I see a show of hands for those of you who tried integration by parts? Okay, you can keep your hand up until I say that you can lower it. Okay, so I have 9 people that tried integration by parts, and only Erin was able to tell me to do integration by parts. That's just mean I'm here talking to a computer and you're not even able to answer. Anyway, you can lower your hands. Integration by parts is the right answer because we want to get rid of the x, right? So in this case, we're going to have x times sine of x. That means we're going to multiply u times v, and I get minus x times cosine of x, and then minus the integral of u times dv. So that means minus cosine of x. So I'm going to change this into a plus cosine of x dx. Okay, and then for the second integral is actually really easy because I just have to find the antiderivative of cosine of x, which I know to be sine of x. So that means here I'm going to have minus x cosine of x plus sine of x plus c. All right, so this is like one of the easiest problems that we can do with integration by parts and trig functions. I think I even solved this one in the example that I gave for the purewise problem. So just if you saw that, then you might have had a head start for this problem. Now for the next one, which was letter F, I'm going to have the integral Who is Jason Dankner? Does anybody know this person? So for the next problem, we're going to have the integral of x times secant of 2x tangent of 2x dx. So you have like a couple of minutes to work on this problem. I'll give you maybe 3 minutes to work on this problem. All right, so maybe by writing in the chat, hopefully. Does anybody know what the first step should be? Should have asked Jason. He had a bunch of feedback to give last time. All right. So if you want to solve this type of problem, again, as usual, you have like a couple of things that you can try. Our usual has been to try first to do substitution. But in this case, if we try to substitute x, that's really not going to help. It never helps to substitute just x. Integration by parts is going to work again in this case, right? Because we have an x over here that seems like it will help that if we differentiate, everything's going to get a little bit easier. And then integrating secant times tangent is actually not too bad because we have that secant times tangent is a function for which we know the antiderivative. So integration by parts should work in this case. So if that's the case, we're going to have that v is equal to x, which means that dv is equal to is equal to dx. Whoops, what's going on? Okay, there you go. Is equal to dx, and then we're gonna have that du is equal to secant of x, secant of 2x, tangent of 2x times dx, which means that u is going to be the antiderivative of this. Now, because this is the antiderivative of secant times tangent, I know that is going to be equal to secant, right? And it has to be applied to the same inside function. Now, the thing is that my inside function over here was 2x, not just x, which means that when I integrate it, I need to divide by the derivative of the inside, right? Because otherwise, I'm not properly finding the antiderivative. You know, like there's a 2 that's going to come out when I find the derivative. So when I take the antiderivative, I need to divide by that 2. So I'm going to have that this is divided by 2. All right, and then I can actually try to evaluate this integral. So the first term after integration by parts is u times v. So that means x times secant of 2x, x times secant of 2x over 2, minus the integral of u times dv. So that means secant of 2x over 2 times dx. Right? And again, this was the whole point. We had that the x that we had originally here in our integral now disappeared because we differentiated it and became just a constant. So at that point, I can evaluate this as x secant of 2x over 2. And then the antiderivative of this. Yes, Charles, there's a question. Oh, yes. So the derivative of secant of x, so I'm re-explaining why there's a divided by 2 over here. So the derivative of secant of just x is secant of x times tangent of x, right? But the thing is that if I have secant of 2x, when I find the derivative of that, I'm going to get secant of 2x times tangent of 2x times the derivative of the inside, which would be times 2, right? So if I just had the derivative of, let me just, if I didn't have this term over here, right? So if I just had secant of 2x and I differentiated that, I would get secant of 2x times tangent of 2x, derivative of the outside, times the derivative of the inside, which would be 2. So I would need a 2 in front of this. But I don't have that 2 in the derivative, which means that it must have been canceled by something else, which is why we have the 2 at the denominator here. Okay, so it's just basically to cancel something that is going to come up once we do the chain rule. Is that clear? Yeah, okay, good. So then the 2 is going to come out, and actually that's really important because it's going to happen once again, once we find the antiderivative of secant of 2x. So when I find the derivative of secant of the antiderivative of secant of 2x, I know that I'm going to get ln of secant of 2x plus tangent of 2x. But this is the antiderivative of just secant of x, right? Which means that if I'm finding the antiderivative of secant of 2x, it should be this, and then I should divide by 2 to counter for the 2 that is going to come out once I apply the chain rule. So same exact logic over here, and then plus c. Okay, so if I find the final answer over here, I'm going to have that this is x secant of 2x divided by 2 minus 1 over 4, because 1 over 2 times 2, times ln of absolute value of secant of 2x plus tangent of 2x plus c. Okay, so it's just a matter of making sure that those constants that multiply the inside function, anytime that you integrate, it has to divide, okay? And that only applies for linear functions, because otherwise we have to do like a full substitution. This is just like a shortcut to not have to do a substitution every time that we have a linear function as an inside function. For the next one, did I have another one? Okay, no, so the next thing that I'm going to do is I'm going to ask you to, so I'm going to present a couple of the identities that we're going to need for this class. I'm going to solve one of the integrals that involves for that. And for tomorrow, I'm just going to ask you to solve 2 problems. So you can keep working on the practice set number 9, but I'm going to ask you to solve these 2 particular problems with which I'm going to start the lecture tomorrow. Okay, so the first thing I'm going to do is to just reintroduce some identities that you need to know for this class. So trigonometric identities. Okay, so this means, so identities means 2 things that are identical, which means equations that you need to know. Okay, so there's 2 types of identities that we're going to need for this class. The first type of identities is just some functions that are defined in terms of sine and cosine, and you need to know the equivalences between a given function and its expressions in terms of sine and cosine. So that should be super intuitive. The other type of identities are what we call Pythagorean identities, and you're going to see what I'm talking about later, but I think you mostly should be acquainted with them. So the first type is, for example, the one that we use for tangent of x. So tangent of x is a function that is defined in terms of sine and cosine, and is given by sine of x over cosine of x. Then, if you do the same thing, you can also write the function secant of x, cosecant of x, and cotangent of x as functions in terms of sine and cosine. So if I write secant of x in terms of sine and cosine, I'm going to have that this is 1 over cosine of x. Cosecant of x is 1 over sine of x. So basically what that means is secant is the inverse of cosine, which means cosine is also the inverse of secant. And cosecant is the inverse of sine, which also means that sine is the inverse of cosecant. And then cotangent is given by cosine of x over sine of x, which is the same as, because this is cosine over sine, and that's the inverse of sine over cosine, this is the same as 1 over tangent of x. So these are all things that you should know by now. Okay, so I think you learned these. You should have learned these in high school, and if not, then you should at least have gone over them last semester. All right, so this is the first 4 set of identities. The next set of identities all come from this first one, which is the most important trigonometric identity, which is that cosine squared of x plus sine squared of x is equal to 1. Right, so that means if I take the cosine of something and I square it, and then I add the sine squared of the same number, I should get 1. Right? So that just means that this x and this x should be the same thing. So this is the most important one. Let me just put a little square around it so that you remember that you need to know this. Now, from this identity, you can get 2 more identities by just doing a little bit of manipulation. So that means if you try to go here and divide both sides, if you divide both sides by cosine squared, is that the first one that I want to do? Yeah, cosine squared of x, then you're going to get cosine squared of x over cosine squared of x, which is 1, plus sine squared of x over cosine squared of x. And this is going to be equal to 1 over cosine squared of x. Okay. Now, based on these expressions that I have over here, I can see that 1 plus sine squared over cosine squared of x, that means sine of x over cosine of x, the whole thing squared. So this I can replace by tangent squared of x is equal to 1 over cosine squared of x, which is the same as 1 over cosine of x, the whole thing squared. So that means secant squared of x. Right? So this is just by using this expression that I have here and this expression over here. So that's the second identity that you need to know. Now, it's important that you know this identity, but keep in mind that as long as you know the first identity over here, this one is really easy to evaluate, right? So it's just a matter of knowing what to divide by, but you know that cosine is at the denominator of tangent, so that should be it. So it's really a lot more useful to know the first identity here and to just know how to get to the other two identities that we're going to have. Then, if I want to do the same thing, but instead of dividing by cosine squared of x, I divide by, here I'm going to do this, I divide by sine squared of x. I'm going to get cosine squared of x over sine squared of x, cosine squared of x over sine squared of x. That looks a lot like cotangent, but squared. Plus sine squared of x over sine squared of x is going to be 1, is equal to 1 over sine squared of x, which is cosecant squared of x. And that concludes the identities that you need to know. All right, so you need to know these three identities. Of course, this is the one that is the most important because everything can be found from that identity, and there is no way around knowing all of these. So you need to know all of them. It's going to come in handy when you're evaluating more complicated integrals. Another thing that is useful to remember is that, you know, sine and cosine always go together. Tangent and secant always go together, and cotangent and cosecant always go together. So that goes as far as to say their derivatives are always similar, right? So like you can see here, secant always goes with tangent, secant always goes with tangent, cosecant always with cotangent, and cosecant always with cotangent, right? So that's really a useful thing to remember when you're trying to evaluate integrals. Okay, so I'll solve, I think I said, one question like this, and then I'll give two problems for you to work on at home tonight. I think that should be in for today. Yeah, so the last thing that we're going to do today is to solve the following problem, which is the integral of cosine to the power of 6 of x times sine to the power of 3 of x with respect to x. So what I suggest now is that you try to do, and here I'm going to tell you, you have to do a substitution. Now the substitution that you choose is going to have to be smart because you're going to have to substitute everything in terms of that function. So I'll give you 2 minutes to start the problem and see what you can do, what might be the obstacles, and so on. 2 minutes. All right, so you're going to have to do a substitution, and now you need to figure out which substitution you should choose. So there's two possible choices, either u is equal to cosine of x or u is equal to sine of x. Can I see a show of hands for those of you who chose cosine of x? Everyone that chose cosine of x, please raise your hands. So I have 6 participants with sine of x. And now, can I see the number, who of you chose sine of x? So if you didn't choose sine of x, lower your hand. If you chose sine of x, raise your hand. Okay. And then 6 people decided not to work on the problem, I guess, because I only have 15 people that actually chose something. All right, so I'm going to go over both possibilities and then we'll see which one actually makes sense for this problem. We're going to see there's only one of them that is going to be useful, and the things that I just explained actually come into play for this type of integral. So two possibilities: either u is equal to cosine of x, or u is equal to sine of x. Now, you could also have tried to use u is equal to sine to the power of 3 of x, or u is equal to cosine to the power of 6 of x. But one thing that we said when we started doing substitution is that it might be, like, it's not really useful to try to do a substitution which you include the power, right? Because then afterward, if you have the complicated thing and the power, just to find the du, you're going to have to do a chain rule. So that defeats the purpose of trying to simplify the integral that we're trying to evaluate, right? So u is equal to cosine of x or sine of x is the only thing that kind of makes sense in this case. And then we can see what happens with that. So if u is equal to cosine of x, we're going to have that du is equal to negative sine of x dx. And if u is equal to sine of x, then that means that du would be equal to cosine of x dx. Right? So that means for this substitution to happen, I need to take out one of the sine of x's that are in the power of 3 over here in order to replace my du. If I want to do this substitution, I need to take one of the cosines that is in the power of 6 to put it in the du. So I'm going to use the two possible splits that we have for that integral to see how we can evaluate it. So the first possibility tells me that I need a sine of x in order to replace my dx. Right, so that means I'm going to have cosine to the power of 6 of x times sine to the power of 3, but I can split that into sine to the power of 2 of x times sine of x dx. So that's if I use option number 1. So that's, yeah. And then in the other one, I'm going to have to take one of the cosines. So that means I'm going to end up with just cosine to the 5 of x times sine to the 3 of x with respect to x. Whoops, no, I still need the cosine that I took out. So cosine of x sine to the 3 of x, and then times cosine of x dx. Right, so this one over here, so this one corresponds to this one, whereas this one corresponds to that one. Now, do I have any takers for either one of them over the other one that could justify why that would be the case? We're almost done, so if I get feedback, you will speed things up. Okay. All right, well, okay, so let's see what we have in the previous page. We have cosine squared of x plus sine squared of x, 1 plus tangent squared, cotan squared plus 1. Yes, I have a couple of raised hands. That's Mark or Parsa. Mark, do you have an idea or a question?
I just left my hand up by accident, sorry.
By accident, okay, then it was just
Yeah.
somebody that left it down. And Parsa just panicked and put it down as well. Okay, no, you have an idea. Okay, Parsa.
Okay, well, if you replace by cosine of x
Mm-hmm.
and you take out one of the signs of x, you can replace it by 1 minus cosine squared of x, the sine squared.
Exactly. So here, now we are left with an even power, right? So, and by having that even power over here, we know that we can use this identity over here in order to replace sine in terms of cosine, which is going to be really useful because we want everything over here to be in terms of u, right? So actually, this is going to be the really important part, which is that the power over here is even, and that allows us to do a substitution properly. In the other case, we have just odd powers, right? So that means that I can't substitute the cosine in terms of sine because this is an odd power, and so this doesn't allow me to do the substitution. Okay, so that's why we are going to go with this one. That's really good, Parsa. So I know that sine squared of x plus cosine squared of x is equal to 1, which means that I can replace sine squared of x by 1 minus cosine squared of x. Weird. Okay, so then I can replace the cosine to the power of 6 of x. And then sine squared over here can be replaced by 1 minus cosine squared of x. And then I have the sine of x over here dx. That sine of x dx doesn't matter that I can replace it in terms of cosine because I know I already have a plan for it. It's already going to become my du, right? So that means I don't really care that it's a sine. I know where it's going. I was just trying to come up with a plan for everything else. So that means this thing is going to become minus du. So I'm just going to put a minus in front of my whole integral. And then I have cosine to the power of 6. That's u to the power of 6. And then I have 1 minus u to the power of 2 d. Okay. So this is the integral that I now have to evaluate. And at this point, it's really easy as long as you remember that you have to distribute and not just take the integral of each one of the pieces separately, right? So that's a really, really important thing. You have to first distribute, then integrate. So I'll have minus the integral of u to the 6 minus u to the 8 with respect to u. And then this will become minus the integral of u to the 6 is u to the 7 over 7 minus the integral of u to the u is u to the 9 over 9 and then plus c. And then I'm going to do two things at the same time. I'm going to first distribute the minus and I'm going to back substitute. So replace u by cosine, which means that I'm going to have minus cosine to the 7 of x divided by 7 plus cosine to the 9 of x divided by 9 plus c. Who was trying to be funny? Mike? If that's somebody's friend, then I suggest that you try not to get your friends to come to my class. Thank you very much. All right, so this is the final answer. You'll have two problems to solve for tomorrow, which are the following two problems. So that's homework over here. I will put, okay, so I imagine some of you are still writing. Yeah, the other two problems are going to be first, the integral of tangent to the power of 3 of x times secant to the power of 4 of x with respect to x. And the other one is going to be just the integral of x to the power of secant squared of 8x dx. Okay, so these are the two problems that I want you to work on for tomorrow, in addition to, of course, working on the practice set number 9 and finishing your assignment for peerwise. Yes, I'll go back over here, and then I'll go back again to the homework. All right, so I'm going to